Okay, so we'll start. Hold on. Today's lecture number 4. The title is Dynamic Resource Allocation. What this one really is about is that in the last lecture we have already introduced the logic used in the system. Right, that's this. Okay. The basic inference rules. And today we are talking about how to turn this logic into a working reasoning system, or how to turn it now, which is logic, which is basically something on paper, into NARS, which is running in a computer. So the system, as you have already heard several times, is called NARS, for non-axiomatic reasoning system. It realized the principle I introduced much earlier about intelligence, which is the belief that intelligence means adaptation under the assumption of insufficient knowledge and resource. So how to turn a logic, not just this logic, but any logic, into a reasoning system? Clearly, you need to turn the grammar rules and the inference rules into programs. So the grammar rules will check, for example, whether the input is in a valid format or not. And the inference rules, like what we covered last time. So each of this kind of rule will become a small program, okay, which you give it some input, it will produce output according to your specification in the rule. So that part is the routine part. Every reasoning system will do that, even though the rules will be different, of course. But there's something else which is not discussed in the logic stage. Usually, there are two major things that you need to address. One is you need to have a memory structure in your computer, so you store all the premise and conclusion and so on. And then you have a control mechanism, which we will see in more detail. Basically, will decide in each step which rule to use, which premise to use, which will decide which conclusion will be produced. So this part is more like a computer scientist work. The previous part is kind of like a logician's work. But in AI, you will have to do both. So NARS is a project started a long time ago. The first version actually I coded in Prolog in 1986. Okay. Since then, there are already, I count roughly, there's more than 50 versions in several program language. In recent years, it's no longer done mostly by me. It's more by my students and cooperators and so on. So this is one version coded mostly by Patrick, who is here. It's a very simple, relatively simple user interface. Well, you cannot really see the detail, just to show you we do have this kind of thing running, which basically have some control mechanism, allow the user control how the system runs and put in new information. And there's some window which shows what the system is doing step by step. And with some additional information, in this case, it shows the memory structure. Okay, very briefly. And the different version, of course, the interface will be different. So today we are going to limit ourselves to the simplest case. Again, this is the picture I showed last time for this overall logic structure. We extend the logic layer by layer, each time with more complicated rules. Okay. The same thing happened, of course, in the implementation. So we are going to, today we're going to only talk about the base layer. Okay. So if you want to write a reasoning system which will implement this fourth layer non-axiomatic logic, or the simplest one which I introduced last time, okay, with this rules and this truth value calculation and so on, what it can do. Of course, what I'm talking about here is a highly simplified version, just to give you the basic idea. But hopefully everyone with basic programming skill should be able to do it if you don't care about the additional complexity and detail, which you will definitely run into. But the basic idea actually is pretty good. We will see. So first, what the system can do. In this stage, it will be a very simple question answering system. So basically, you can give the system two types of sentence. This is also something we covered last time. The first layer this is the grammar of the first layer. There are two types of sentence. One is what we call judgment, which is basically a piece of new knowledge or new information, or you're telling the system something. Another type is questions. You're asking the system something. So it's basically this two type of questions you can put in. Then the system will just answer questions according to its available knowledge, of course. This is basically the same for all question answering system, even though the mechanism within the system are quite different. So here, every input sentence is taken to be a task to be processed. Okay, so that's the word we use in ours. Basically, a task means something you need to handle, which is kind of similar to in many other systems called a problem to be solved. That's the same thing. And how to answer a question or how to process a new judgment, well, is all using the beliefs of the system. And in this context, we use belief and knowledge as the same. Some philosopher will say, no, they're not the same. Knowledge confirm the belief and so on. Well, we don't make that distinction, okay? And of course, later we'll see, actually in ours, what we usually call belief, knowledge, hypothesis, guess, and so on, they're basically all the same. There are some small difference in terms of, the level of confidence. For example, low confidence one typically called a hypothesis. A more sure one, it can be even called a fact. Okay, but the difference is relative. There is no absolute difference between belief and knowledge. So now let's see. If the input or the task to be processed is what we call a judgment or a piece of new knowledge, what the system will do? Well, in traditional knowledge base, this is relatively simple, right? You just remember it. Whenever you get a piece of new information, you just remember it. In ours, is much more than that. Of course, it will try to remember it. That's of course. But there are two more things. One thing is it will try to use it to revise the existing belief, which match it. This is a normal situation in ours. Actually, last time we also talked about the revision rule, okay? Because we do not assume a new experience, in this case, a new judgment, will always conform with your previous knowledge. That's not assumed in ours, okay? Because it's open to the new environment, insufficient knowledge and resource in this context, it just means the new thing may be different from what you believe. Okay. So in this case, we are going to use the revision rule, as I explained last time. So that's what this part means. Another thing which also make it different is it will do simultaneous forward reasoning. Forward reasoning is what we covered also last time with this kind of rules. Okay. With two pieces of a given, you derive a new conclusion. In this case, actually, today I will make this more concrete. There's two premises, typically in most of the case. One is the previous knowledge, what the system already know. The other one is a new task. That is a piece of new knowledge. Okay, we can just, to make things simple, we can just think this. The first one is a task to be processed. The second one is what the system already know. In this case, you'll see that you're not going to do a revision because they're talking about different things. Okay, you already know S as a type of M. Then I told you that M is a type of P. Then you're going to do forward inference. This one sounds pretty straightforward, but it makes a big difference. Later we will see that when we talk about, say, for example, natural language understanding, that's a big topic today. In today's research, not in today's lecture. Okay, I'm not going to say much more about that. One aspect is when you communicate with other people, what you get typically is not only the literal meaning of that sentence, it's also what that sentence means, okay, or its implication. That's typically need to be figured out by combining that with what you already know, and you derive something. Okay, that's typically the case. In slightly even more complicated communication, that's you always get the intended meaning, not the literal meaning only. So how can that happen in this kind of system? Well, you not only remember what I told you, you also think about what it means by combining it with your other knowledge. That's how it's handled in us. Okay, so this is very different, like compared to traditional knowledge base, which just remember it. And the other one, I think, is more, it's easier to understand. That's the kind of like everyone's doing, how to answer a question. Okay. You give it a question, first, it will try to match it literally with an existing piece of knowledge. Okay. For example, again, here we know there are two types of question. I mentioned that. It can be a yes/no question. It can be a like what type of question. Okay. If it's a yes/no question, it's nothing but a statement without a truth value, which is interpreted as I'm asking the system to tell me the truth value of that sentence. So in that situation, what the system does, well, clearly it just simply match the question with its knowledge about that relationship. If there is a match, then it will probably report an answer, which is the truth value of that belief. But of course, in ours, the situation can be complicated. Later, you will see that sometimes for the same question, it may get several different answers from different sources according to different evidence. Then what? Then I will need to go back to the rule we covered last time again. This is where this choice rule is used. Okay. What if you have two answers for the same question? Well, you'll pick the one which is more reliable with a higher confidence. Okay. Roughly speaking, okay, there are some more complicated factors involved, but roughly speaking, if you have more than one answer, you'll pick the one that's most reliable. Okay. What if this is a question which contains a variable to be instantiated here? Okay, for example, I'm asking you, what is a bird? Give me an example of a bird. So that's the case which match into this pattern. So the predicate is a bird, the subject is what, which is kind of like a variable term to be instantiated. Okay. So in this case, again, you may typically have multiple answers. In this case, you have, let's assume you already know more than one type of bird. So in this case, which one is better? Again, this is something we covered under the name of the choice rule. We are going to somehow combine the two factors in the truth value. We want something which is have more positive evidence, less negative evidence, and also have more total amount of evidence. We want to balance those factors and get big answer. Okay. So that's basically this part. Okay. So we are going to try to answer a question by belief, which of course is the simplest case. For a slightly more complicated situation, you don't have a belief which perfectly match the question as it is. And that's where you begin to do reasoning. Okay. So again, this is, now you can see, that's why I keep the last lecture note open, because now you can begin to see where or how the rules are used and what situation you want to use which one. Okay. So in this case, what we're talking about is the so-called backward reasoning. You have two premises. One of them is what we call a judgment, or you can call it a belief. That's a statement with a truth value. The other one is a question, which is a statement without a truth value. Okay. So you want to know whether M is a type of P. And what you already know doesn't directly answer it, but it tells you S is a type of M. So in this case, what do you generate? You generate new questions. And this is something I mentioned last time. Under the condition that if any of the new questions get answered, their answer will be combined with the belief to do forward reasoning to answer the original question. Okay, we do it this type of thing all the time. Okay. We start from the goal, or the final answer we want to get. Okay. You gradually reduce the problem or question into derived questions, which you can eventually answer. Okay. But after that, it's not done. You still need to go back to do forward reasoning. Why? Because in NERSC, all the truth value calculations are carried out when you're doing forward. This is one place which makes NERSC different from many other traditional reasoning systems, which if you know, like say Prolog, which basically work in the same manner. So in binary logic, whenever you finally derive, you solved all the derived questions, the original question is already automatically solved. But in multi-value logic, that's not the case. Not only NERSC, but any logic which need to do calculation for the truth value, you need to go back. So for those of you who are familiar with computer science, you see this is very much like recursion. You start at top level, you go all the way to the bottom where all the derived questions are answered, but you still need to go back to the top to have the final answer, in this case, to do the truth value calculation. Okay, so we are not going to go into that detail. Just show you that this is basically what is going on in the implementation. Everything is reasoning. Eventually, the purpose is to answer questions. But even if a piece of new knowledge, you will still want to do reasoning on it, even though this is not a question, but you kind of like prepare yourself for the future related questions. Okay, so you try to figure out what's the implication. At least that's one of the motivation. But later we will see there are other motivations. Actually, forward reasoning contribute to the system's attempt of self-organization. The system tries to reorganize its knowledge in a more effective way to summarize its experience for the future. So that's basically what the system will do. And let's see an intuitive picture. Again, that we already mentioned the last time. In the first layer, every statement is nothing but two terms related by a copular, which has a direction, means inheritance, what we call it, inheritance. So that means, for those of you familiar with graph theory, the memory is nothing but a big, directed, weighted graph. So you see, in this case, each of the nodes correspond to a term. You give it a name. Then each of the link has a direction, even though the arrowhead, some of them are relatively small, not very easy to see, but there is a direction. Okay, it's from, the convention is from the subject to the predicate. Even though inheritance actually goes in both directions, we mentioned it before. Okay, in one direction is inheritance of extension, in the other direction is extension, inheritance of intension. Okay. But they traditionally point from subject to the predicate, and each link has a truth value attached to it, which in ours, there are two numbers, right? Not one number. Again, that's something we discussed before. The first one is called frequency, the second one is confidence. So that's the whole thing, okay? What is really new today? First, you see the color, right? Now we have two types of links, the black one and the red one. As you can guess, the black ones are the beliefs, or the knowledge the system have already accepted into its memory from its past experience. Then the red one are the tasks. There are several ways to tell the difference. The task, you can think the task is the active component. That's what the system is thinking about at the moment. And the belief and the background knowledge. Well, that's one way to think about their difference. Another way is to think about their type. All the beliefs are judgments. That's a relation with a truth value. Task, on the other hand, as I said, there are two types. One is like this one, has a truth value. That's a piece of new knowledge. I'm telling you that Swan is a type of swimmer, and I'm telling you that's the truth value, which actually you can see, I'm saying that's not the case because the frequency is relatively low. Okay. But a question can also be a link without a truth value. Here I use a question mark to indicate, I'm asking the system whether Robin is a type of swimmer or not. Okay. But you see that the black things will not be labeled with a question mark because of the beliefs. You must already know, right, where to be believed. And some of you may wonder, can the system remember a question? Yes, but that's a different story. Okay, we are not going to go that far. So for now, just to make things simple, there is a huge number of the black links and a relatively small number of the red links. Just to give you some intuitive idea, you can think this, the black thing is kind of like in the millions, and the red thing is kind of like only a few dozens. Question?
So would you have both of the red links at the same time, or
you actually have more than one task active at the same time? Later we will talk about
okay.
that. Yeah, that's a normal situation. So that's the.
I have to ask you. Because I was thinking you can put it. I was thinking about this confidence. When you have this belief, why is this 0.9? Or did you put it in 0.9, or this is results that is 0.9?
So the question I think is, where are the numbers come from in the first place, right? In the first place, actually, there are two types of scenario. One type of scenario is the new task is what we call a judgment, which come with a belief, which come with a truth value. Typically, that's the situation where the input itself is, say, statistical by nature. And it's already statistics. I tell you that this data is a summary of, say, 100 data points, and the success rate of this inheritance relation is 75%. Okay, so you just put that number in. But the most common situation later you will see in our demos and so on. We are using actually binary truth value in our daily communication, right? We don't use numbers. That's actually at the very beginning, the AI people don't want to use statistics because that's unnatural. We respect that. Okay. what we do, very simple, we just use the default value. Okay. So if you use our system, if you just say, I'm telling you that, say like in this case, a swan is a type of bird. By default, well, as you can guess, that's why there's so many, 1 is a frequency, 0.9 is a confidence. That's the default truth value. Okay, so if you just give it a positive statement or affirmative statement, it will automatically take those 2 numbers. Then people will say, oh, how can you justify that? The justification is basically human language is very approximate. When we say something is true, we are not actually claiming there is no negative evidence. It's basically say for the current purpose, we don't care about them. Okay. So when you make a positive statement, then the system will assume you're providing positive evidence only. Okay. So that's the simplest case. And why 0.9? Actually, this is a system parameter. Believe me, it doesn't really matter. As far as they're all the same. It's kind of like all the inputs, unless you make special adjustments. Initially, they will be believed to the same level. And whether that level is really 0.9 or 0.8, 0.7, it doesn't really matter too much. Okay. But if you really want to make a difference, you're allowed to specify that. It's kind of like I'm telling you, not only I tell you a sentence, I stress that this is really true. Believe me, okay, better believe me, this is crucial. Well, if you want to do that, say, for example, you can give NARS a confidence level higher than the default. You can say it's 0.99. But of course, we have already mentioned, it cannot be absolutely true. NARS will not take it at all. Okay, 1 will not be accepted as a valid truth value. But if you want, you can say 1, for frequency, confidence, I want 0.999999. That's okay. That's okay. That will be quite stable. Okay. Of course, that also means that at this stage, if we only have layer 1, the system will initially believe whatever the user provide to the level that user specified. Which of course, in the future, it will not always be the case. Okay? You don't have absolutely trusted tutor or user in normal situation. Okay? You may later you'll see that we develop multiple information sources. The system may actually believe one source more than another. So even if you tell the system this confidence is 99999, the system may actually say to itself, okay, I don't completely trust you. Okay, I think it's probably only 0.8. One important point to remember is whatever it is initially, it doesn't matter too much because it will be adjusted according to the system's own experience. Okay. Even if you give it a whole bunch of things which with a high belief level, with a high also frequency or a very low frequency, there is always a possibility for the system to gradually change its own opinion. So your opinion is just a reference or a starting point, which is kind of like, yeah, just like a human being, your parents, your teachers will have a higher authority compared to ordinary people in terms of, give you information. But it's a matter of degree. Okay, and it can be changed. So that's about the initial situation, especially the red one. Okay, the red one is something that is given to you from outside. And the black ones are already absorbed into yourself, and you already adjust them according to your previous knowledge. For example, in this case, you'll see between this swan is a type of swimmer, you actually have a contradiction. Okay, according to your previous knowledge, well, let's see, someone told you Swan is a type of swimmer. But now you have a new one, which is basically saying no. That's unlikely to be the case, or most of the evidence is against it. And the confidence actually, for some reason, is lower than this one. Here, this is just an example, so I'm not going to explain where this number comes from. Let's just say, oh, it's a less reliable source. Okay. If that's the case, then what? Then if this one and this one get selected, of course, the revision rule will be used. So the result will be some type of compromise. Okay. Between this one and this one, but closer to this one because this one has a higher confidence level. Okay. You can actually check using our truth value functions, and you can try different numbers and you see what's the result. But for today's discussion, that's not crucial. So we will just say, okay, that's the case. So that's the tasks, that's the red ones, beliefs, that's the black ones. What is concept? Concept is like something like this. It's a node plus all the links directly point to it or point out of it. Or in graph theory, it's called all the incoming and outgoing links, or in link and out link. Right? So you can think this as a data structure. The term is the name of that data structure or the identifier of that data structure. And the content, what that data structure contains, is its relationship with the other things. Okay. This hopefully explains to you what I said in the second lecture. I said the meaning of a concept in ours is not a reference in the world. It's what it knows about that. So this intuitive directly tell you that's indeed the case. That's not just a philosophical claim. Okay? So what BERT means? Those four links to the system at the moment. And this also explains why in ours it's very natural to show and explain the meaning change of a concept. So obviously, each time you add a new link into it, you change the meaning of the two concepts that linked by that a little bit. Okay, clearly not completely because the meaning is not defined or specified by any one single link. It's by all the links put together, roughly speaking. But you still change it a little bit. And also, if you change the truth value of a link, you change the meaning of the concepts related by that link a little bit. Okay, so that is why everything in the system change. You see, this is like a network, but this is not clearly not like a neural network, not to mention how to make the link. At least on the top level, you can see first, the topological structure change. Okay, at the very beginning, the simplest implementation as you can get, the memory is completely blank. It's empty. There is nothing. It's an empty graph to start with. Okay, so your first input is going to create two concepts with a link in between. And your second link, well, it may change that and may introduce another pair with a link in between, and so on. Okay, so gradually, so now you can see why we have a picture like this. It will be a very complicated network. And this is actually a very simple example. We will give you this. So in reality, you cannot really follow the dynamic change, but it just gives you some intuitive idea about what's going on. So when the system is running, new nodes get created, new links get created, both by the new input as well as by the system's own reasoning activity. Okay. Like, for example, yeah, I give you this and you use this one and this one, you derive something here. Okay. That will be added into the memory, which will also change the system's knowledge and the meaning of the concepts involved. Okay. So we will say more about that, but that's the basic picture. And you can also see it's not really hard to implement this picture at all. You just build a weighted, directed, simple graph. Well, yeah, the only thing that's not so simple compared to what you learn in graph theory is possible in ours between a pair of nodes have more than one link, and they don't necessarily have the same weight value attached to them. Of course, the reality is more complicated. We have other information associated later we will see, but this is the most fundamental picture about the memory structure and about how we use the word task, belief, and concepts. Okay.
Can this be an undirected graph?
It cannot be because this inheritance relation, say, bird is a type of animal and animal is a type of bird. They have different meaning, right? So that direction is crucial. But of course, some other relations are undirected. For example, similarity relation. Say A is similar to B, B is similar to A. Usually, we take them to mean the same thing. Okay, so there are some directed graph, directed links, also some undirected links. We have both, but the direct one is more fundamental. So that's why they're introduced first. So in the first layer, all the links correspond to inheritance relations. So everything is directed, but we have undirected introduced later. But not today. Today we will just stay with this picture.
I just got that out because the bird and an undirected ones.
Now here, everything is directed, even though the arrowhead, some of them is not easy to see. Okay. This is just because this is an example only for the first layer. Yeah, like here, you don't see it, but there is arrowhead. Now, if you understand this, you can also, if I really challenge you should be able to figure out how the system runs. As soon as we start, okay, you can say there are two processes going on. One is NARS is supposed to be an open system, which I said from the very beginning, which means that new input can come in at any moment. And we have an input channel, which is always open. And in the simplest case, there is only one input channel, which only come from one user. Okay, so you can just type in things at any moment. And so that will get added into the system initially as a red link. Okay. Another thing is, at the same time, the system is always running in the background. You don't have to say run. Okay. Conceptually speaking, in reality, of course, you have a command to start it. But the system is always running in background, even when you're putting things into it. Or in other words, even when you're telling the system something, the system also is thinking about it at the same moment. So
I'm thinking like if you're not typing anything on the keyboard and you're just away from keyboard, as they say,
it will run.
Well, what is it actually like doing?
We will talk about it.
Yeah, okay.
So now you see the first process is pretty straightforward, right? Whatever you tell, and it will be turned into a link, it will be put into the corresponding concepts. If there's no such concept, it will create one, right? It's just a new node correspond to the term you mentioned. So that's pretty straightforward. The second process is relatively tricky. That is, besides accept new input, what the system does. As I said before, it does task processing. Basically, it will actively working on the red links. The black links, most of them are irrelevant. It's just stored there. They will be invoked whenever they become relevant. But the red one are what the system is really working on. So, roughly speaking, you can think the basic process is this. You pick a red link and you try to process it. And I have already said, to process it means what? Of course, depend on the type, whether it's a piece of new knowledge or it's a question. Okay? But no matter what, you will see actually the process is the same. So whenever you pick it up, The first thing you want to check is whether there is a matching black one. Like for example, in this case, there is a red one, there is a black one. Both of them starting from the same node and ending at the same node. So that's clearly a match. Okay. So a match may happen between a question and a belief, or a judgment and a belief. And if it's judgment and belief, you do revision. You kind of like merge these two into one. Okay? And if it's a question with a belief, you just directly answer it. So that's pretty simple. But what if you pick a red one, you pick another black one, doesn't completely merge with it, but share a common term with it. Like for example, you pick this and this, then guess what? That's what we talked about last time as syllogistic reasoning. Remember those triangles I draw? Okay, you always use this tool to form two edge or two sides of a triangle. You make the third one. That's your conclusion. Okay, you will see all of our reasoning have that picture. Forward, backward, they all fall into that picture. That is, you're given relation between S and M and P, then you build a relation between S and P. It just, the direction may be different, the truth value calculation may be different based on different combination, but that's the logic part. For the control part, you just pick two, you build a third one. What if I pick this red one and I pick this black one? They do not share anything, okay? Just this one and this one. You see, according to the logic, there is no direct conclusion from this two. So that is a very, 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 very nice property of what we call a term logic or Aristotle logic. That is, the typical inference rule require a common term, which start as a logical requirement. For computer scientists, it will save your system, okay? Because it naturally limits the scope of your selection in each inference step. That is why, unlike many other reasoning systems, in ours, there is no search. You're not looking for an answer. You select an answer. Meaning what? Meaning for this question, for example, I know all the knowledge I can directly use at this step must have either a robin in it or a swimmer in it. Then naturally localize the scope of my selection from the whole knowledge base to two terms or two concepts. Okay, you don't have that property in predicate calculus or propositional calculus. This is one major reason for me to pick term logic. Because as someone trained in computer science, I directly see, okay, clearly it will save your efficiency. It will greatly increase your efficiency. Okay. It will guarantee that if you just pick something within the same concept with yourself, I mean a task, you can derive something, you can have inference rule, derive something, and also it's a meaningful combination because they're semantically related. Also, you see, last lecture I mentioned about a traditional problem for the paradox of material implication. Okay, in logic, that triggers the study, the research of so-called relevance logic. That is just how to guarantee what your premise and your conclusion are related. In predicate calculus, propositional calculus start with, from any A and any B, you can derive the conclusion A implies B. Okay, In ours, you cannot do that. So now you see, okay, given that description, the task processing become pretty relatively simple. What you do for a given task, no matter whether it's a question or a new piece of new knowledge, and if it's a question, no matter it's a yes, no question or what question, you just make it to interact with certain beliefs which stay in the same concept as you, step by step. So conceptually speaking, in each step, you only think about one belief. And then the next step, you pick another belief. That's it. And nothing else. How about the inference rules? That's another very important design principle or feature of NARS. You don't pick the rules. This is very different compared to many other reasoning systems, especially the one that use multiple strategy. For example, we have already seen in ours, you do deduction, abduction, revision, induction, and so on. So for a given task, the natural question is, which one I want to do first? Well, you can say you don't make that decision in ours. It's completely determined by the task and the belief you picked. Remember the picture I draw last time? Again, this kind of pattern. Now you can think this is a task, this is a belief. As soon as you decide this two, what type of reasoning will be decided by them? Accurately speaking, decided by the location of the shared term or by their combination. Okay, if the shared term is the predicate of one but the subject of the other, what you're going to do is deduction or is opposite, which is called exemplification. Okay, if the shared term is a common predicate, what you're going to do is abduction in both directions. If the shared term is the common subject, what you're going to do is induction in both directions. Okay, this is the opposite of this. What that mean? That means the reasoning process in NARS is completely data-driven. When I give the system a question to answer, the system doesn't think, oh, I should do deduction or I should do abduction. The system instead will think what I know about that term. Okay, they pick a belief, and if that belief say, oh, I can do induction, then you will do induction. Or actually, it's not that belief that say that, it's the combination of the belief and the task. Together, they decide what the system is. Okay, this is very important. Later, we will see more about that. So they will decide applicable inference rules, and you can already see here the applicable rules is not necessarily unique, but it's limited. In NARS, I think the most complicated scenario is we may have, for example, 10 rules for a given pair of belief and task. Okay, but not for today. For today, at most we have 2 because there are more layers to be added. So anyway, it's a fixed number for each given combination. It's predetermined. Okay. But you don't make a choice about which one you want to use at this point. So now you see, if we focus on a single task or a right link, what the system will do about it is completely determined by the black links that's selected to be used on it, as well as the order of that selection. Okay, That's the one that's actually, in a sense, similar to what we call an algorithm, which will process this task and will decide the final answer. So now you see another thing I often say now, I think it makes sense, is math has a logic part, has a control part. Now you can say what each of the two is responsible for. The logic part decide each step. Okay, after you pick this tool, what will be the result? That's completely determined by this kind of table. It is fixed. But on the other hand, if I give you a task, how to process it, to a large extent is determined by which premise you pick or which belief you pick as a premise to use with this task. That's not determined by the logic. The logic allow all of them, like in this example. If we only talk about this task, I'm asking you whether Robin is a type of swimmer or whether Robin can swim or not. With the given knowledge, what the system will do? Well, there are several possibilities. Okay, if the system pick up this, then it's like the system is thinking, oh, you're talking about Robin, huh? I know Robin have feathers. Have that have anything to do with whether it can swim or not? You see, this combination is going to produce the third edge of this triangle between these two. In this case, is a derived question that the system is asking itself, whether swimmers all have feathers or all feathered creatures can swim or not, whether I know that. If there is already an answer, then that will answer that question, which will indirectly answer the original question. And you see that in this case, there is no answer for that question. The same process will continue. Say, okay, we'll think about what is related to this one, either from this point of view or from, say, oh, bird are feathered creatures. Okay. But why you want to pick this one? What if I happen to pick this one? You ask me, Robins are swimmers or not? I say, I have no idea about Robin. I don't know much about that thing, but I know Gao can swim. And then what? Then that will create a link between these two. That the system is going to ask itself whether Gaos and Robins are somehow related to each other. You'll see, that's what I'm talking about. The logic does not decide how to solve that question. The logic only say, as soon as you pick this tool, you cannot escape from the conclusion. Okay, that's something the logic force to produce. But which way you want to go? That's the control part. Okay. So what is the challenge of this insufficient knowledge and resource in this context? First, insufficient knowledge. If you have all the knowledge, which means that for every possible question the system may face, the system already know what is the right order. Or in that kind of graph, it's kind of like already know a path. You'll see another way for people who are familiar with graph theory. You'll see each of these questions will actually be answered by looking for a path between these two nodes. Using the existing belief as edges. Okay, in graph theory, that's basically what it is. The only difference in this kind of graph is it can go in the opposite direction of an edge. If you are doing, say, induction or abduction. If you only do deduction, you only follow the edge direction. Okay. So that's a graph theory type of explanation. But clearly, there are multiple paths. Which one you pick, that's the control problem. which one can exist? That's a logic problem. Okay. So what is the challenge? The challenge is you don't know what is the best task. If you know all of them for all the questions, you have sufficient knowledge. Okay, here you don't. Especially when we say we have a novel question or a novel task you have never seen before. You don't really know how to do it. Here, you, I mean both the system and the designer. Okay, we do not anticipate all possible tasks when we design ours. Insufficient resource means what? You cannot do exhaustive search, even though the graph is always finite. Okay, and in theory, you can try all possibilities. It's finite, but the NARS is supposed to work in real time, so you usually don't have the time to do that. Even though people may say, from the given example I just showed you, yeah, that graph, I can actually exhaust all possibilities. Yes, you can, but that's a very special trivial situation. In general, if you have millions of concepts, you cannot do that. Then what you can do? You don't know where to go. You cannot exhaust all possibilities. How about we do some planning or training in advance? Well, even that is impossible because the situation may change. Okay? Even if you, from given information, you train the system so that it can answer some question according to a predetermined path, when the situation changes, your knowledge is no longer valid. So the traditional machine learning approach also does not work in this case. Or planning in advance. Okay, some planning is possible, but you don't know all possibility, and you don't know all the change that may happen. The other extreme, some people say, yeah, how about we just do random choice? Okay. Well, actually, some people explain human creativity and flexibility using a random number generator. I never believe that. Okay. Why? Because they're not adaptive. Okay. Adaptive means that you need to respect your past experience. You try to use it as much as possible. Okay. Random, arbitrary in this case means that you ignore your past experience. That's not a good idea. Even though sometimes, yeah, if you really know absolutely nothing, then every choice is equally random or arbitrary. Well, but that's a special case. And usually the meaningful situation is the experience, your past experience tell you something, but not the full story. So you still should use it, but not completely trust it or depend on it. That's at least that's the attitude we are taking in this research. So this not in a too extreme situation. It's neither completely no information or complete information. Okay? It's somewhere in between. So this is actually quite typical for artificial intelligence. In a sense, you can say from the very beginning, ideas like heuristic search is exactly introduced to handle this type of situation. Okay, so in that spirit, they are not that different. But the technical idea, of course, is very different. What NARS does? There is one thing I think I have already mentioned. It's the price we pay. Is we already gave up the hope or the premise or the guarantee that for any given problem, we will find the best answer. We already given that up just because it's sufficient knowledge resource. Okay, you cannot promise that. But on the other hand, it doesn't mean everything goes. What the system try to do is to achieve all tasks as much as possible according to its experience, or it's always trying its best. That's one part I think is understandable. Another thing is the question already raised. NARS typically have multiple tasks, and not just a few. Okay, a certain number. Usually, typically, I will say, usually in the level of hundreds, okay, more than a couple of dozen. Why? because not only the user can keep giving it new questions, it will derive much more by itself using the inference process I just explained. It will try to think even for one given question, okay? It will try to think in multiple possible directions, then each of them will be a new question it asks itself. Okay? So it will be a large number, but compared to the number of belief, of course, is still a very small number. That is the red link, black link thing I just mentioned before. So what to do? And that's a concept I first introduced in my PhD dissertation. I call it controlled concurrency. It's not really a fancy idea. It's very easy to understand. Is to do what? Parallel processing. If you know multiple possibilities to solve a task, you try all of them in parallel. So first, we don't call it parallel, we call it concurrent. You know, in computer science, we keep this small difference, tricky difference. It's not say we have multiple processor, what we can in today's world, but that's a different story, okay? We are now saying that we have multiple CPU, which actually allow all the tasks to be processed at the same moment. Instead, it's like in operating system, it's called time sharing, right? You know, that's the idea I learned from my operating system class. You do A little bit, then you do B a little bit, then you go back to A, then you go to C, then you go back to B, then you go to D. Well, that's how our today's computer, cell phone, and everything works, right? So for a user, you have multiple processes going on, but within the system, at any moment, in the simplest case, there's only one CPU. Okay? Everyone is taking turn. You have a queue, right? Everyone is taking turn. That's a very old idea. If you don't know it, actually this idea was introduced in the context of AI. It's actually introduced by John McCarthy, okay, who invented the phrase of artificial intelligence, who also raised the idea of time sharing, which will later become at the foundation of operating system and many other computer software. So the idea is very simple that many people claim, you know, the human brain is highly parallel. You have multiple neurons which can fire at the same moment. But computer, at least traditional computer, there's only one processor. Some people say, yeah, because of that, you cannot be truly intelligent. Now we know that's not the case. If you run fast enough, there's concurrency and the real parallel processing from a user's point of view. Very often, you just cannot tell the difference. So
what's the benefit of framing the problem in a concurrent manner if you don't have parallel hardware?
You will see.
Okay.
So what you have learned is what I said, time sharing in operating system is called concurrency, which to computer scientists is already known for many years. What makes it different here? Why this cause a difference between parallel and sequential, even though in reality it is sequential? First, I do it in NARS, it's very natural. Because you see, to do time sharing, the basic idea is to cut a complicated process into steps. Okay, you can do one, and you interrupt there, and you switch to another. Then you can go back to rebuild the context and then continue this. Sometimes it's tricky, but in a reasoning system, it's very natural. As you can guess, each slice, time slice is what? Is one single inference step. Two premise, one conclusion. That's one slice. After that, next step is what? Well, I can change my idea. So an inference process consists of multiple inference steps. Every step is specified by the logic, but the logic says nothing about which step must be followed by which other step. So it makes it very natural to use one single inference step as a unit of this concurrency. So it's kind of like in my previous picture, I have two red link, okay? I do 3 steps here, then I do 2 steps there, then I go back to this one, I do 5 steps. To the user who only focus on this one, only see I have done 8 steps. In the middle, I run away, I did something else. Who cares? Of course, later we'll see it actually matters, but the basic idea is here. So what's the benefit? The benefit, the key benefit here is I can do parallel processing conceptually with different speed. That's the key idea in the control mechanism, which make it different from the other reasoning system. You can see, again, if you really go into detail, you see, oh, that's not really a new idea. You steal it from operating system. In operating system, the process have different priority. They have multiple priority queue. Usually in most of the operating system, something will be finished first before you can have the time for something else. Right? So the idea is already there, but in ours, the situation is much more complicated. In your operating system class, you are already told, there's some task called, what is called processor hungry, or different book use different term, or it's more computation, calculation heavy or something. So that kind of thing will use most of the time in operators, in the CPU. And some other process, for example, if you connect to a printer, usually, the printer is much slower, so the operating system does not give too much time to that process because you need to wait for the printer to finish the first step to do the second step. So they typically have a lower priority. Okay, so that's basically determined mostly by the, say, hardware and the nature of the process. In ours is different, even though the idea is the same. Now we are giving every task a priority value. A priority value will decide, later we'll see how much resource it will get from the system in this time sharing process, like in my previous example. Okay, I have 3 tasks, only one CPU. Then let's just say I have A, B, C. A have top priority. B have intermediate priority. C has the lowest priority. What the system will do? System will do A, then B, then A, then C, then A, then B again, then C again, then A. See the difference? In the long run, A, B, C are running at the same time, but A runs much faster. In the same unit of time, say 1 second. A is processed 20 steps. B goes 5 steps. C only goes 2 steps. I think that's not hard to understand. That's the secret, the key secret of inference control in ours. Okay, that's how it is handled. So how to do this A, B, C? Well, the current idea is to use probabilistic selection. Say like using, again, on the example I just mentioned. I have A, B, C. I select them according to a probabilistic distribution. Say the chance for me to get C is, say, 60% each time. B is 30%, okay? C is 10%. So if I keep doing this with the same distribution, you will get what I said. So in each time, whether you get A or B or C, doesn't really matter. What matters is in the long run. A gets 60% of the CPU time. Okay, B gets 30%, C gets 10%, exactly according to the priority distribution. So now you see, oh, there are two selections. How about the belief? Now you can guess, it's the same trick. Okay, for bird, I know 500 things, like in that node, okay? There are 500 blacklings. Now I'm thinking about one question, which one I should pick? Well, same story. Each of them have a different priority. You pick one by chance, but not the same chance. Okay. Then you pick a task by chance, then you pick a belief by chance, then this combination will have a chance to happen. But as soon as that is selected, it becomes deterministic. What conclusion will be derived is completely determined by logic. There is no chance involved anymore. You get a conclusion. Then what? Then you put the conclusion back, you do the same thing again. Forever, until the user stop the process, stop the whole system. So you'll see here, this is what I already said. Here, the key is not use probabilistic selection. Some people say, oh, because of that, your system become unpredictable because it's you throwing a dice and each time picks. That's just the implementation detail. The key idea is to do parallel processing with different speed, and furthermore, that speed can be adjusted. It's not like in operating system, everything related to printers will always have a low priority, and everything related to CPU or cache will have a high priority. No. Now you will see, oh, now I see all the tricks will be in the priority values. Yes, that's true. The priority values or the priority distribution, to be accurate, is a factor that actually decide how a task gets processed. You see, a task is processed by the sequence of beliefs selected for it, and that selection is determined by priority distribution. Again, why I stress is the priority distribution, because priority is determined relatively. Say, is 0.5 a high priority or low priority? It depends on who else is competing with you, okay? If all the other guys at 0.9, 0.5 is very small. If all the other guys are 0.1, you're the highest. So what really matters is the priority distribution, which is determined by what? That's a story we cannot really answer, just because a priority value in this mechanism is a summary of all the factors we have been taken into consideration. And that go back to the title. That's why this lecture is called Dynamic Resource Allocation. The reasoning process, the control mechanism, is all about resource allocation. You have limited time. What do you want to think about? You cannot think about everything. Okay? The idea, you can say, is coming from, in terms of implementation, is from operating system. On the theoretical side, of course, it's from psychology. It's human attention allocation. What gets your attention? You don't pay attention to everything, even though some people you're told to say, okay, you should think about everything. But everyone knows that's impossible. Okay, whoever try to do that cannot survive at all. You simply don't have the time. So the priority in this context decide your chance to be used. Or you can think about it as the rank in resource computation. This idea also not only come from psychology, operating system, you can also say it also comes from evolutionary computation. Say like genetic algorithm, if you're familiar with that. They simulate the evolution process where the key idea is you need to compete for the limited resource. And you have a rank, which based on your past performance. And if you rank high, you can get more resource. Otherwise, you get less. It's the same idea. Or you can even say it's related to economy. Okay? So how to decide the priority? Well, we are still trying our best. So our priority value functions are the one that's the weakest, I guess. In the design, in each version, we try to modify it. But on the other hand, it's not arbitrary. It's kind of like summarize our knowledge, I mean the designer's knowledge about how it should be done or what factors should be taken into consideration. Okay? I can just mention a few of some, for example, tasks. Clearly, initially the user can decide the urgency. The user can tell us several tasks at the same time, but give them different initial priority value. It's kind of like I'm assigning 3 assignments to my students and tell them this one is urgent, that one you can keep in your mind for 3 years, I don't mind. And that one you may have to spend your whole life to think about. Okay, we run into that kind of scenario. So the belief very often is the usefulness. As I said, for bird, 500 things. Okay, but a feature like bird can fly, which make it different from many other animals, that's one of the most used feature for bird. Let's just assume that's the case. Okay, but for some other people, maybe it's because bird lay eggs. That's more important. But anyway, it's based on the system's past experience. It's going to adjust its priority from time to time based on whether it's useful or how useful it is.
So basically, like if you already experienced answering 10 questions and taking this link first usually is the fastest way to answer the question that in the future gets higher priority.
Exactly. We know we all learn in that way, but also sometimes it's misleading, right? It's a bias, but it is very often it's a necessary bias. Okay? If you successfully solve a certain problem in a certain way, then you try to use that method more often than the others. But here, again, we use probabilistic selection. It doesn't mean I have to always use that until it completely failed. It's just that one have a much higher chance to be bringing into my mind compared to the other less used. Okay? Clearly, of course, that's only one factor. Relevance to the current situation. Okay, I have 5 million concepts, but in any moment, of course, I'm not going to allow all of them active in my mind. Okay, then otherwise it will be crazy. So I will only focus my limited attention to the thing that, again, according to my own judgment, consciously or unconsciously, to be related to the current scenario. Okay, I will spend my resource there more than somewhere else. So no more detail. And also, as you can see, as situation change, your distribution also need to change. That's why it's called dynamic, right? So there is a decay process or forgetting mechanism in ours from the very beginning. Okay? Simply because you cannot think about everything. And what you think to be important at this moment is not necessarily important in the next moment. So all the priority mechanism values decay in a certain way. Okay? Until it reach a base level, which is completely determined by its own quality rather than by its relevance to the current situation. You see, relevance is something that changes over time. Quality does not. For example, truth value, confidence over belief. Okay? Everything else being the same. A high confidence belief is more useful than a low confidence, of course. Just like a fact is more useful than a guess, right? Everything else being the same. So that's the quality. That will decide is kind of like a base value of its priority. Another thing I don't have it in my list is the simplicity of everything. Okay, because of limited resource, simple things always remember better than complicated ones. Everything else being the same. and so on. If you analyze each of them, you'll see, oh, there's nothing tricky. This is common sense. But the problem is not many AI systems taking those common sense into consideration. Okay. We are trying to use as many as we can. So eventually, you'll see that there are two forgetting mechanisms in NARS. One is what we call relative forgetting. That is, everything become low priority or low priority values over time, unless later you'll see that there's something bringing it up. Okay? You activate it. Otherwise, it will just go down, but it will still be there. It just gets less and less time. On the other hand, another resource is space, storage space. You'll see, compare NARS to many other systems. NARS produce much more junk than everyone else. Okay? Because many of the inference tools, they give you a large number of low priority things, which may or may not be useful, and most of them actually are not useful. The problem is, at the very beginning, when you produce them, you don't really know whether they will be useful. You leave it for time to decide. Okay? Think about ourselves. I will claim we are doing the same. Not when you get a new idea, very often it's determined much later whether it's useful. So when you produce so many things, then what? You run out of space, then what? Of course, there's also a simple solution. You delete the one with the lowest priority because according to your current judgment, they're the less valuable. You can get it wrong, just like us, right? Forgetting mechanism is very annoying, but it's absolutely necessary, even if you often get it wrong and you forget important things. It just is that moment you don't know. Okay. What else can you do? Remember, everything is definitely a disaster. Many people still say that computer is better than human, computer never forget. Well, that's why it's stupid. Okay, that's one reason. It doesn't manage its own limited resource. It depends on the human user to delete files. And NARS will manage its own space, even though it can get it wrong. So now you can see, basically I have already finished it. I will just summarize what I've said. We introduce a new data structure called a bag, which is a data structure, you can call it a probabilistic priority queue, okay, which is repeatedly used to manage time and space at the same time. It has constant size, and each time you can put in something into it by specifying a key value, just like traditional data structure, and a priority value as I defined. When you take it out, there are two different ways. You can take it out using a key value, just like in ordinary, say, hash table or something. This is unique in NARS. You can select something, like in priority queue, but it's not a deterministic priority. It's not the highest priority that will get selected always. It's probabilistic. It's just the highest priority will have more chance to be selected in this. So now you see a concept like the node in my previous graph contains what? It has a name, that's a term. It contains a task bag, that's the red links, and a belief bag, that's the black links. Okay, all of them have priority value attached. And the memory, this whole graph is what? It's nothing but a bag of concepts. Okay, now you see all the nodes also have priority value, okay, which of course is left out of that previous diagram, otherwise it would be a mess. Then the whole NARS in this simplest implementation is what? It's just a memory, an inference engine, a task buffer, and a user interface. It's shown in this simple diagram, okay? And here I have a rough description about what I have already said. Input come here. Each of them is just two nodes linked by inheritance relation, or here I even have this symmetric version, which we call similarity. They're all put into a buffer first. This buffer has it's basically a bag I just introduced, has limited space. Okay, if you overload the system, of course you can do that, but the low priority thing will be automatically deleted. Then what? This is a selection point. As I said, it's a probabilistic selection. So it will pick one and put it into memory. This memory is the graph I have explained. Then in each inference cycle, it will pick two links, a red one and a black one, which is not colored here, but they share one common term, feed into the inference engine. Inference engine is pure deterministic, it's just all the rules. Some of the rule will be triggered by this combination, will produce results. Results are put back here into the buffer again and join the computation for the next round. And some of them will be selectively reported to the user. For example, the best answer for a given question or a surprise conclusion, which have a very high priority and confidence, may be reported to the user. That's it. Keep running. As soon as you start it will run. So what I mean, I think I have actually already explained each of them. You don't have a predetermined algorithm for a given question or a given any given input task. Okay, how it will be processed is completely determined by what the system knows and all the priority distributions there. And also it changes from moment to moment because of the feedback and so on. So just repeat it, the actual processing path for a given task is determined by the beliefs selected to interact with it, which clearly usually is not all the beliefs possible. So it's data-driven, context-sensitive, and unpredictable and unrepeatable. Even the same task, if you give it again to the system, usually the process will be not exactly the same. So when to stop? Well, of course, eventually a task will stop being processed. But it's not because it's completely solved. There's no task which is completely solved enough, normally. It's because its priority is low enough to be removed. You just simply forget it because it's no longer competitive with the others at the moment. So the theoretical consequence is what? Is to talk about computability and computational complexity at the task level doesn't make sense anymore in us because it does not follow a predetermined algorithm at that level. Okay? If you talk about for each inference rule, of course it's just an algorithm. And the complexity is also very low. Actually, it's a constant. Okay? So this is a simple diagram which compare NARS in this aspect with traditional computation and the machine learning. Traditional computation is represented by Turing machine. The capability does not change over time. It's perfectly repeatable. Okay? If you repeat the same question again and again, then you get the repeated answer and the same computational complexity or the same resource cost. That's in the definition of computation. Okay? Machine learning is different. Okay? Its capability will increase when you train it, but eventually it will converge to a stable input-output mapping with fixed computational complexity. Okay. So it's approximate computation at the end. So what we are doing is, that's why I don't call NARS a learning system. I call it an adaptation system, adaptive system. Actually, it is a learning system. It just now learning have been used in this sense by many people. Okay, but in NARS, you'll see the learning process never stop and never convert to anything. In general, okay, for a specific task, it may or may not converge. You don't know. It depends on the future. And finally, there is such a thing called superintelligence, which I don't really believe. That's why I put it in mark. Some people think singularity, superintelligence, AGI, they're all the same thing. To me, they're completely different. Okay, I know how to do AGI. I don't know how to do superintelligence or singularity, and I don't even believe those things can be done. Okay, so that's another story which they don't have the time for that. Okay. So now you see that why my first book is called Rigid Flexibility. And this is the title of the book, which I don't like, but because they come out from a book series, I don't have a choice, right? They all use the same cover. And what I have in my mind is something like this. You see, every step is fixed, okay? But the overall shape of this chain can be anything. So a logic-based system can be super flexible. I even claim my system is more flexible than deep learning, even though it's based on solid logic. That's two different things. That's also why I like the reasoning system framework better than the others. On one hand, it gives solid justification for every step. On the other hand, it gives you complete freedom to combine them into a sequence. That's all for today. So let's take a break. Then we will have some discussion.
About 10 minutes break, okay?
Yeah.